Welcome to Math 201. Let's get into the first topic. We're going to start with section 2.1, the tangent velocity problem. It's not actually covered on any quizzes or exams, but it's a good motivating problem for what we're going to be studying. Look at problem 1. Pause the video right now and read problem 1. So we have a position function f of x for the car, right? After 0 units of time, it's traveled 8 meters. After 1 unit of time, it's traveled 15, etc. So we could, create a little table for the position functions. We could also graph it, right? But anyway, the question is, what's the instantaneous velocity of the car at time x equals 3? Well, look at problem 2 now. All right, pause the video, read that. So here, it seems like whether we're looking at problem 1 or problem 2, it might be in our best interest to graph the function. And this is a pretty approachable function, right? Y equals x squared, right? That's a quadratic, right? I hope we know this. This is a y equals f of x. Okay? And problem number 2, what's the slope of the line tangent to the curve? Well, if you remember, the tangent line, right, this is, of course, 8, right? Because if you plug in 0, you get 8. And try to draw this to scale. This is 3. Right? So if we were looking at the tangent line to the curve, then we have something like this. There it is, right? Now remember, the tangent line, right, that's the line that just touches the curve at exactly one point. It grazes it, right? So that's the tangent line to the curve y equals f of x at x equals 3. Okay? Problems 1 and 2 look completely different, but it turns out they're actually the same. They're completely the same. They're worded differently. Problem 2 is a visualization of problem 1, but they're really asking the same thing. And to see that, we're going to have to learn a bit of calculus. The solution, by the way, I don't want to keep you hanging. Or maybe I should just say the answer is this, of course. That's an M, by the way, lim, right? All right, that seemed good to you? No? Well, if not, maybe this looks a little better. No? No good? Well, anyway, it turns out the answer is 12. Units, I guess it's meters per unit of time. I don't really specify. Okay? How did I get that so quickly? Well, you have to do a bit of calculus. In a week or so, you'll understand. First, we have to define limits. So the expression lim x arrow a f of x equals capital L means L is the limit as x approaches a of f of x. Okay? i.e., as x approaches a, f of x approaches L. And that's a pretty good definition. You'll actually see that in some of your web assigns. But really a better definition would be to say, we can get f of x as close to L as we want by making x close enough to A. And I'll just say without equaling, I'll just say, without equaling A, right? We never want to let x equal A, but we can get it arbitrarily close to A. Okay, that's what the definition of a limit is, right? And in order to really understand what this definition is, I have to give two little sub-definitions, and I promise you we'll get to examples. We can define a left hand and a right hand limit. So the expression limit as x approaches a from the left, right, that little minus sign of f of x equals L, means, well, it's the same thing as before, except means L is the, I guess I'll just, well, it's the left-hand limit, but I guess we could just say it's the limit as x approaches a from the left of f of x. Right? Same exact thing, but we've got this from the left component, right? So this minus sign here gives us this little bit of detail, right? That just means that x is always less than a, right? We're not considering the case where x is greater than a and approaching a from the right. So in other words, this is saying, I guess we'll say for x less than a, as x approaches a, f of x approaches L. Right? Now again, this right here is what the minus sign means, right? We're considering only values lower than a. And then you might imagine we've got the opposite of that, right? That's a plus sign right there. Limit as x approaches a from the right of f of x equals L means, well, you know, I'm just going to go ahead and copy all this, right? Why not? Because it's completely analogous. And we just have to change a couple of words, right? We have to change from the left to from the right. And we're not talking about x being less than a. From the right means that x is greater than a. Right? And so what this means is that for x greater than a, as x approaches a, so as x gets smaller and smaller toward a, f of x gets closer and closer to L. All right, so enough of these examples. Let's do the most basic kind of example we can, where we draw a graph and we examine the graph, okay? This is really just going to appeal to intuition. So let's go ahead and draw a graph and see what we get here. We're going to have this, maybe this. I guess we'll do one more, something like that. Okay, and this is y equals f of x for some function f, right? Really be a piecewise function, right? So anyway, we have a couple of values of interest. I'll call this a1, or no, maybe that's a little complicated. I'll just say a, b, c, d. Call this e. I'm going to call that f because that's our function, but g, right? We'll say that. All right, and I guess got a couple of interesting values here. Maybe I'll call this value capital L. This will be capital M. Maybe this will be capital N. And maybe this will be capital O. Okay, so let's take a quick look. We're going to look at the left-hand and right-hand limits, okay? So let's see. Yeah, what color should we choose? Maybe we'll do green. Or maybe we'll stick with black for right now, okay? So the left-hand limit, right? The limit as x approaches a from the left of f of x. What's that going to equal? It equals, oh, whoops, I don't even think I had a value for that. Huh. Call this guy P, of all things, right? So it's going to wind up equaling P, right? Well, it turns out that's actually the same thing as x approaching a from the right, right? Because no matter how we approach a, whether it's from the left or the right, the function is approaching the same y value, right? Now, let's take a look at the next value. Left-hand limit, right, as x approaches b from the left, right? What's that going to equal? Well, we might be tempted to say, oh, that looks also like it's p or something like that. But you'd be wrong. It doesn't matter where we get to. It matters what we're approaching, right? If we're approaching b from the left or from the right, to be honest, doesn't even matter. We are approaching this value, right? L. Okay? It doesn't matter where we get to. It doesn't matter what f of b equals. It matters where we're going. Okay? Now, in this case, right, for c, the left-hand and right-hand limits are going to be different. And in fact, they're going to be non-existent. Right? Because the left-hand limit for x approaching c equals negative infinity. The right-hand limit for f of x equals positive infinity. You can write a plus infinity if you want. All right? So this is the first case where the left and right-hand limits don't equal each other. For d, well, it looks like, once again, the left and right-hand limits do equal each other. Right? And they both equal m, right? Again, that's where they're going. It doesn't matter that we never actually get there. It doesn't matter that the hole isn't filled in. We are approaching m, even if we don't get there. E is just sort of a kind of a trick question. It looks a little weird, but actually, it's just n. Right? No tricks there, right? Equals, was that n, right? And same for the right-hand limit. I don't have the space, so I'll write it down. And then last but not least, we have g, right? The limit as x approaches g from the left of f of x. And this is kind of interesting, right? This one equals p, right? But if we take a look at the right-hand limit, what's that going to equal? It's O. So if your function's kind of unusual, then your left and right-hand limits might not be the same. Now, let's take maybe two more looks, I'll say. One or two more looks at limits using graphs. Or maybe, well, yeah, graphs / calculators, let's say. Maybe I'll try to use both. So let's consider a function that we actually know, right? In this case, x squared plus 5 over x squared minus 4. I said find the limit as x approaches 1. Well, I don't actually know what that graph looks like. So number one, I'll draw it. We can look at the graph. But suppose that we didn't have the graph. I'm going to define f of x equal to x squared plus 5 divided by, oh, whoops, sorry, I didn't want to do it that way. That's annoying. But we want to say divided by, oh, yes, we have to be a little careful here. Let's do parentheses, x squared plus 5 divided by x squared minus 4. And now we can delete the parentheses just because they're kind of an eyesore, I think. Anyway, that's our function. I strongly recommend defining f of x equals, and then going ahead and creating a little table here, maybe. right? So we got a table here. So what we're going to do is we're going to let x1 be a value close to 1, but less than 1, right? Because we're approaching 1 from the left. So if I say let x1 equal 0.9, then for y1 I can say, okay, what is f of 0.9? Is it going to give me that value? Yeah, if I click on the graph. You know what, I don't even like that. I think I'm just going to go ahead and do this. Let x1 equal 0.9, and we're just going to find an f of 0.9. All right, so we get negative 1.82, blah, 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 blah. All right, so we'd fill that in for our chart there, right? There, and I'll fill it in a sec. For f of, actually, maybe I can just do that right now. I'll say negative 1.82-ish, okay? For f of 0.99, okay, well, that's a bit closer to 2, I guess. Negative 1.98-ish. And if we just sort of keep doing this, well, what do you know? We're getting, I don't want to say it's exactly 2, but I think you can kind of see the pattern here. Right? We're getting so close to 2. Right? That it looks like we're getting closer to 2. Okay? And anyway, you can try the exact same thing on the other side. All right? We can do f of 1.1. Record that. Okay, and then we could, I guess, do f of 1.01. Getting a little bit closer to negative 2, I guess. If we just sort of keep doing this, well, I think you can see where we're going with this. And then last but not least, well, sure enough. Okay, so we have that. So it certainly looks like, if we go back to our thing over here, as x approaches 1 from the left, it certainly looks like limit as x approaches 1 from the left of our function equals, looks like it equals negative 2. And it looks like that also equals a limit as x approaches 1 from the right of our function. Right, now again, we didn't prove this, but the evidence strongly suggests it. And in fact, to even suggest it even more strongly, what we can do, I don't know, why it zoomed in, there we go. If we want to go ahead and take a look at the points, let's see what we have for just 2 comma, or no, I guess it's, sorry, it's 1 comma f of 1. Now remember, we're not actually considering f of 1, but we just want that sort of rough area. It sure looks like we're getting close to things, right? So if I, for example, change 1 to 0.9, 0.9, see how we're just getting arbitrarily close? All right. Well, yeah, see, it doesn't even distinguish. Let's see if we do it like this. There we go. Let's try that, okay? So we'll just quickly screenshot this, crop it. All right, and we're just gonna stick this in the notes real quick. Right, so picture just kind of confirming that, right? Right, now, here's why we're doing all this. We say that, keep this on. We say that the limit as x approaches a of f of x equals L if the left-hand limit, right, that limit as x approaches a from the left of f of x equals the right-hand limit, right, the limit as x approaches a from the right of f of x, and they both equal L. Otherwise, we say limit as x approaches a of f of x does not exist. Maybe I should probably do it lowercase. And I just write DNE. So I'll leave this one to you to try that. Now, one thing that you'll see when you try that, I recommend pausing the video, trying example 4. Again, I strongly recommend downloading Desmos or going to www.desmos.com. It's free. I think you might need to give them an email address. That's about it. One thing you might notice is that in order to find a limit, we don't have to plug in values arbitrarily close. We can just plug in x equals a to f of x, right? So we can just find f of a if it exists. Okay? And so then that begs the question, oh, well, does that always work? Well, what if we tried, for example, 6, right? Well, if we just plug it in, then we get 2 squared plus 5 over 2 squared minus 4, and that's going to equal 9 over 0. No good. Okay, well, then I guess we have to go back to the graph, right? Well, if we take a look at the graph, what do we have? Oh, no. Let's do this. Oh, I don't know why it zooms in like this. There we go. If we take a look, what is happening as we are approaching 2? Well, if we have, let me just get rid of some of these guys right here. If we just have the line x equals 2, right, maybe we make this a dotted line. We see that whether we approach it from the left, it looks like we're approaching negative infinity. From the right, we're approaching positive infinity. It's looking like this limit is not going to exist. And again, maybe I could just quickly screenshot that graph right there. Let's just crop that a little bit. There you go. I think that's good enough to illustrate what's going on. Alright. And that'll be all for today. I'll make another video of the guided practice.